In this section, we're going to be looking at dependent means or dependent samples, and we're going to be looking at hypothesis tests for these. For the most part, I think you're going to find that these are most suited for before and after type questions. So that's what we are going to be looking at for the most part. Let me write down the hypothesis test itself, and you'll see it's very similar to the previous ones. Most of the hard work or most of the computational stuff you won't have to do. We can let your calculator do that part. But once again, here's the first thing we need to do is verify that the samples are random. But dependent. So as I said, before and after is really what we're going to be looking at here. And the populations are normal. And we're going to make that assumption for all of this, but technically there either need to be normal or the number of items in the sample needs to be at least 30. State H0 and HA. Specify alpha. The degrees of freedom will be n minus 1. Use the T table for the critical values. And then what we're going to do is we are going to be given the data on the sample, and our job will be to compile the data, and we need to figure out the mean of the data that we're given. So we'll be looking at a difference or a mean of differences. You'll see this notation will make sense in a minute. So that'll be what we use for the mean, and you'll have a standard deviation for the sample that's the same formula that you've had before, although you won't need to memorize any of this because the calculator will let us do these things easily. And then we have the test stat. And you can see even that looks quite similar to the ones we've done in the past. So you have a sample mean, and then you have a population mean, all divided by a standardized standard deviation. And then finally, number 8, make the decision. All right, here we have an example where students take the SAT score, and then to improve their scores, they take a class to help improve them. And so the idea here is to determine whether the class helped them or not. And the first thing before we set up any kind of anything is to get our sample statistics. And they're given right here. But what we want to put, we want these numbers, but I actually want the difference of these numbers. So I'm looking for a column or a row that I'm calling D, and that's where I'll take the first minus the second, here. So I'll get like negative 100, and then I'll get negative 70, and then I'll get negative 50. Notice that they're all negative because the students, well, if you take a class to study for the exam, after having taken the exam, you should do better. You could write all these down, but I'm not going to bother with that. Let me show you instead what I'm going to do it with. I'm going to bring up your calculator, and you can enter the data directly like that. So what I'm going to do, go to the Stat button, And the first thing you're going to want to do is probably clear everything that's in your stat. So if you look at your, if you go to edit, like number 1 here, and I hit the enter key, it's cleared. However, if it's not clear, what you have to do is use number 4, and then you have to tell it which column to get rid of. You may have more things than one to get rid of, but for this, let me see if I can find above the stat. There's a thing called list, and that's what that is. It's the list variables. If I can choose them from here, so if I choose number 1, so I've got my L1, and if you want, you can put more things. All you have to do is separate it with a comma, so I can go ahead and put like L2 if I just had too many things in there, if I had a bunch of lists. Then this will allow me to clear out everything at once, and you can see it says done. Now to enter our statistics, we click on stat. We want number 1 for edit. This is where you put your stats in. And at the bottom here, you can see that it's going to give us, this is the list of numbers. We'll get this. For the first one, that's 300 and 400. I want its difference, so I can do 300 minus 400. And if I hit enter, it puts the difference in there for me. So I don't have to bother with actually doing the subtractions. And I understand this is not that big of a deal, but when it comes to something like decimals or fractions and all that kind of stuff, you may find this very useful. Now, if you are watching this, I am going to enter all of the data. Now, what I do is I notice while I'm doing it, I'm looking at data item 4, and I see data item 4 matches what I'm typing, so I just want to make sure that I don't lose track. This is probably better facilitated with some sort of a program, like a spreadsheet program would be much better for this kind of stuff. But all you have is your calculator, so it's the next best thing, I suppose. Like I said, I'm going to enter all the data, so if you want, you can certainly fast forward through this particular section and wait till I'm done, because I don't plan on talking anymore until I get it all in. Let me clear this. Number 7, I think I made a mistake. See, this is why you keep your eyes peeled on that 7 and make sure on the right one. 420 minus 450. Enter that. 370 minus 400. Uh, 320 minus 390. And then finally 410 minus 450. And I got them. So, and it says L111 means I'm on item 11, which makes sense because I've entered my 10 items. Now, what I want is the mean and the standard deviation of this sample. So let me click Stat, and then arrow your way over to Calc, and then just hit enter because you want the one variable statistics. And it's going to pick from list 1. You don't have to put anything for this. This is only if you had more than one thing per item, and they were all just one item. So you can enter your way out of this. And it gives me my info. I've got a mean, X bar is negative 60. So in this though, in our notation here, that's D bar. And then the standard deviation is also listed in there. Let me have you back. Don't use the sigma x, use SX. That's the sample standard deviation. And that's the one that has an n minus 1 in the denominator instead of just an n. That's the one that we want. Which reminds me, I think I wrote the definition of S sub D down wrong, but let me go ahead and take the 27.8887. I'm going to take that. Let me scroll back up just for a minute in case I wrote down that. Yes, I did. This was a common thing. People often wonder. The reason why that's an n-1 is complicated, and I can't really explain it to you, but you need it in there. So if you are to do this by hand, you need that n-1 there. I went an extra decimal place. I like to do that while I'm doing the work. So anyways, what we have, let's actually do the problem then. Here's what my claim is. Let me do it like I do all the other ones. Let me write my claim down. Is there enough evidence to support the instructor's claim? So what is the instructor? He claims that the course will improve test scores of students. So you have a test score, and he figures the next version of it will be better. So if that's true, the first test score minus the second test score will be a negative number. So he's claiming that the mean difference is negative, meaning that there is a difference between beginning and end. Not just a difference, but better than before. So let's call this mu sub d is less than 0. That's what it means for the second score to be higher than the first score. And we have our sample stats. That's all I need, my sample. We had the mean was equal to negative 60. It's just called, you can call it an X if you want to, but the D's there tell you that it's a mean of differences. The sample standard deviation. And we need the number of items, so that's 10. And we want to test the claim at alpha equals 0.01. Since no standard deviation for the population is given, I may assume that it is unknown. I also instructed you that every single problem here says that the populations are normal, so we don't have to worry about the size of n. We can just go on to the problem itself. As usual, I'll do it in two fashions, the classical method versus the p-value method. Let's start with the classical method. We need our null and alternative hypotheses. Since the strict inequality is the claim, I put that into the alternative hypothesis, that there is the claim. And notice that makes a left-tailed test. Remember, the t distribution is a lot like the normal distribution. It's a bell curve and it's symmetric. So the null hypothesis would be mu d is greater than or equal to 0. So let's see how this works. Well, the first thing we need is a test statistic. So alpha equals 0.01. Not test, I'm sorry, I did it wrong. I need to get the beginning of the critical region. So alpha equals 0.01. The degrees of freedom will equal 10 minus 1, which equals 9. That's enough to use the table. It's also enough to use your calculator. I think what I'm going to do, since they're giving you an area, you want inverse t, because you're not interested in area, you're interested in t naught. So from this, t sub 0 will equal, I've used the table enough, I think you can figure it out, but I'll use the calculator to show you how it works. Let me uncover the stuff that I have. So for this, what you want to go is, remember, second, and then click the vars button because it's the distributions that I want above it. Turning on the calculator first is a good idea. Second, the vars. And then, like I said, I want number 4. I want the inverse t, because I am looking for a t value. Now, it wants the area. Now, the area here, this is a left-tailed test, so if I put 0.01, that's correct because it only wants the area up from the left up to the point. The degrees of freedom then is 9. And then you can enter your way out. And there's the instructions. Negative 2.821. Let me write down that what it was on your calculator. And I want to make sure I have it in the right order. You put the area and then you put the degrees of freedom. So the area first, and then the degrees of freedom, and I got negative 2.821. You can alternatively use the table, the T-table. If I pull that thing up, being buried behind a bunch of stuff, even behind the calculator, there it is. On this, let me increase the size. You want one tail, and you want to do 0.01, which is the fourth column, and 9 degrees of freedom. You can see it says 2.821, but we needed the negative since we're talking about a left-tailed test. This table doesn't tell you that information. You have to infer it. So anyways, let's do our T-stat. I should probably draw a picture of this. Let me make that dot a little more vigorous. This is way over there. And in here, that little region right there is 0.01. So the test stat, T, will equal d bar minus mu d all over s sub d divided by the square root of n. Let's put in all that information. My d with a bar over it was negative 60. Mu sub d, like normal, is 0. S sub d is 27.8887, and then divide by the square root of 10. Now on your calculator, watch how I enter it. Let me have you back. I'm going to start with the negative, so don't forget you can't just put minus, you have to put that little negative, 60, and then divide. Now since I have a complicated denominator, I'm going to put it in parentheses. So I get my 27.8887 divided by the square root of 10. Remember, you've got to get out of the square root, so you've got to hit the right arrow there. See how it ended the square root, and then you can finish off the parenthesis. If you sneak a parenthesis under the square root sign, it'll mess everything up. So let me hit enter and see what happens. I get negative 6.803. Well, there's no question that that is most certainly in the rejection region. So I reject H0, which sounds kind of bad, but realistically, the claim was that the differences would be negative. So when you say reject H0, you're saying that H sub A was probably correct. H sub A is the one that was saying that they would do better on the second test. So this statistically says it's pretty likely that they are probably doing better on the second test than on the first one. Now, if you were prone to use p-values, you do it this way. You, of course, start with the t statistic, and we got negative 6.803. Now you're looking for area, and you want the area to the left of that thing. So what we do for that is you go back to the DISTR, and this time, since I'm talking about area, I want a cumulative distribution function, and that is number 6, a CDF. Now, we want to go from negative infinity, which is already there, to negative 6.803. So put negative 6.803. I need the degrees of freedom. That was 9. And remember, let me put that down. We have T, C, D, F. You put the lower limit, negative infinity, then the upper limit, and then you put the degrees of freedom. And this gave us approximately, let me see if I can write it down, 3.939 E negative 5. Well, it doesn't do you much good if you don't know how that actually stacks up to a number. That E negative 5 means you move the decimal to the left 5 places. So you end up with 0.12340 zeros, 3939. And then alpha, if you'll remember, was equal to 0.01. So alpha is quite a bit bigger. P is less than alpha, so that means that you reject H naught. And if you remember, in this particular case, rejecting H naught means that the training that was given between the exams was probably successful. All right, I have another example here, just like the previous one. In fact, we've got 10 items just as before. And the first thing that I'm going to need to get out of that sample is the mean of that sample and the standard deviation of that sample. It really doesn't matter if you do before minus after or after minus before, but you need to understand how that makes your hypothesis test, because it will probably change it from a left tail to a right tail or vice versa. Let me go ahead and put these things in, but I'm going to put their differences in. So this here then, well, let me go ahead and get the information, and then we'll worry about what it's asking us. So to put those in, click Stat. Now, I only put things in L1, so I'm going to clear my list. And then I'm going to go second, find list above Stat, and then enter your way out of this, and it cleared L1 out. So when I hit Stat and then Edit, I can go ahead and enter the data into L1. So remember how we do this. 67.9 minus 67.8. And then it puts the one data item in there. In fact, when you do this, it's almost like the two samples didn't matter. It's really equivalent to us just having one sample, and we just called it D instead of X. So this is really like our one variable statistics from the review. And once again, I am going to enter all this data, so if you want to fast forward, go right ahead. All right, after you've got all your data, remember then press Stat and to go over Calc, and then choose the one variable stats. That's all we need. L1 is the list, and you can just enter your way through the rest of it, and it will give you the information you need. My X bar is my D bar. That's negative 1.7. And then my S sub D, that's the SX1 on the calculator, 4.019. I'm going to say 4.02. That rounds to 4.020. So those are the informations that I need, and N is equal to 10. So let's go ahead and get the claim. All right, let's actually read the problem now. We have the pass completion percentages of college football quarterbacks between their freshman and sophomore year. So they should get better between their freshman and sophomore years. Is there enough evidence to support the claim that, okay, so the claim that the pass completion percentages have changed. It doesn't say better or worse, it says has changed. So we indicate that with mu sub d not equals 0. So this is a two-sided test. And our stats, let's get those things in. We have, this would be our sample stats. Let me write that down. Our sample stats was that the mean was equal to negative 1.7, S sub d is 4.020, and n equals 10. And we're going to test this claim at alpha equals 0.1. All right, I've got everything I need as far as the calculations are concerned. Let's go ahead and solve this. Let me go ahead and get my H naught and my HA. Since it's not equal to 0, we'll say mu d is not equal to 0 will be in H sub A. So that's two-tailed test. Then H naught will be mu d equals 0. So there we have those two things. Let me go ahead and get my T naught. So for T naught, we have alpha equals 0.1. Degrees of freedom will equal 10 minus 1. That'll equal 9. And you can use your calculator or it. But this is a two-tailed test, so this is a little more complicated than before. Let me draw a picture first, I think, of what we're trying to do. You remember on two-tailed tests, you have to divide alpha into two equal pieces. So you'll have a 0.05 at one end, and then you'll have a 0.05 at the other end. So this right here, we need to do alpha over 2 equals 0.1 over 2. So you can do that. Now your calculator is very interesting. What you can do here is simply specify that from negative infinity up to my point, we'll have an area of 0.05. Watch, we're doing the t-test, remember. So since we want a t-value, we want the test that is inverse t. That's number 4. I made a mistake there. Let me clear that all out. And you got to watch this. Let me get back to it. Number 4, inverse t. All right, so the area is 0.05. The degrees of freedom is 9. Enter your way out. And I get negative 1.833. So let me write this down. Now the beauty of this distribution, though, is that you know the other value is positive 1.833. Alternatively, if you wanted to get the 1.833 on your calculator, then what you're going to have to do is specify the area all the way up to it, which is 0.95. So for that one, you can actually do this. NVT equals 0.95, 9, and it will give you the positive version of that number. So you can do that or just use symmetry. All right, and remember at the end of this test, when we do the p-values, we're going to have to multiply everything by 2. But now let's go ahead and do our test statistic. The test stat, that's t equals d bar minus mu d all over s sub d divided by the square root of n. And that is d bar, where did you go? That was negative 1.7 minus 0. SD is 4.020 divided by the square root of 10. And let's see what our calculator gives us for that. So we have negative 1 0.7 divided by, and don't forget to encase the denominator in parentheses, divided by the square root of 10. And then don't forget to get out from underneath the square root and end the parenthesis. Enter. I get negative 1.337. So where is that? Negative 1.337. If I see, it is not in the rejection region. So we fail to reject H naught. For p-values, if you choose to do this method instead, we start with the t-value. And then you're trying to figure out the area that occurs, well, in this case, since it's a negative number, I would look at the area that occurs before it, since you're going to be adding up that area plus an equivalent area on the right-hand side. So let's go ahead and see what this gives us. So let me go to t. Since I want an area, I need the cumulative distribution. So I need number 6. And now we want to start from negative infinity and go to negative 1.337. And then the degrees of freedom is 9. And enter your way out of it and see what we get. I get 0.107. So what this gave you, let me just this thing here was what it gives you. It gives you 0.107. I don't know if that rounds to that or not. Okay, so that's to one decimal place, 0.107. That's not quite the p-value. The p-value also adds this. So that's also a 0.107. So the p-value is actually 2 times the number that my calculator just gave me. And you can do this so easily. Check this out. All I have to do if I want to multiply this by 2 is simply hit times 2, and it will automatically take that answer and multiply it by 2. So I get about 2.214. If you recall, alpha was equal to 0.1, and so we have that p is most definitely greater than alpha, so we fail to reject H naught. And before I finish, remember, on a two-tailed test, p equals this plus this. Okay, the last example here, let's go ahead and get our statistics. And you're really going to want to clear out your entries this time, because while you can overwrite the previous entries with more entries, if you write it with less entries, there's to delete things. Well, let me show you. I think it's probably easiest if I do this. There's 2 ways of clearing these out. You can do it the one way, or you can go in here. If you go to edit it, I think you can start hitting the delete button on your keyboard or on the calculator, hitting the delete button, and that will just delete them. So there they go. And then you can start anew. Well, let me go ahead and get these in. And as usual, you can go ahead and fast forward through this if you don't want to watch it. Remember, I'm doing the first minus the second for each of these entries. So after you have your data entered, go into Stat, and then choose Calc, the second one over, one variable stats, and we want to get the SD. Just enter your way through this. We want the D bar and the SD. D bar, 8.2375. And S sub D. The S sub D is most likely not exact, but 5.2225. I think I'll round it to 4 places. My guess is that is matters almost not at all, but you know, when you've been doing math as long as I have, you get a bit OCD. So let's go ahead then and take a look at what is the claim that they're telling us. All right, so we have 8 contestants try to lose the highest percentage of weight in order to win a cash prize. They have an obstacle course. So an obstacle course, the idea is that you should get better at it, which means that your times should have decreased. So let's see what happened here. Is there enough evidence to support the claim that the contestants' times have changed? Oh, that's it. I'm going to change this word, by the way. I remember now why I chose this thing. Improved. That's the word that I want. So erase the last word if you wrote the whole thing down and put improved. That's what I want. So the claim is that the difference between the beginning and the end is greater than 0. So this is what it means to say to say these times have improved, because the time would be less next, which means time is improved from the first to the second, which means if I take the first time minus the second time, I'll get a positive number. So that's why mu d greater than 0 is the right thing to do. And then the stats, this is the sample stats. I keep forgetting that these are samples. Sample stat was D bar was equal to 8.2375. S sub D equals 5.2225. And then N equals 8. Let me get our null and alternative hypotheses in here. So for that is an alternative hypothesis, that is the claim. And that'll end up being a right-tailed test. And H sub 0 is that mu d is less than or equal to 0. And once again, let's go ahead and do the, this is a one-tailed test, so I don't need to divide alpha over 2. Alpha was what? 0.01. You know what I should have said up here in the question, test the claim at alpha equals 0.01. So now, since it's a right-tailed test, there is 0.99 amount of area that is up to that particular point. Let's see, degrees of freedom equals 8 minus 1, which equals 7. So since I want a T0 value, let's go to the calculator. So this is a right-tailed test, which is a little bit different. Let's go to my distributions. Now, since I want a T value, I want number 4 for inverse T. How much area? If you put 0.01 here, it's going to give you the area that is all the way to the left at 0.01. I need the 0.01 to be all the way at the right. Let me draw a picture. What we want is this. I want this piece over here to be 0.01. That means up to here is 0.99. That's what your calculator needs. It's the area from negative infinity up to the T0 value. And right there is T0. So let's go ahead and go back to the calculator and get my information in. The area is not 0.01, but 0.99. And then the degrees of freedom is 7. Enter your way out of this. and I get 2.998. So let me see what the command was for your use. INVT 0.99, comma 7. So we have our rejection region. Let's go ahead and do our test statistic. T equals d bar minus mu d, all over s sub d squared divided by the square root of n. D bar was 8.2375. Mu sub d is assumed to be 0. S sub d was 5.2225 divided by the square root of 8. And let my calculator handle all that for me. Let's see, 8.2375 divided by, don't forget to put that stuff in the denominator in parentheses. Get out of the square root and the parentheses. So approximately 4.461. Let's see where that lands. Oh, that is inside of there for sure, isn't it? So we reject H naught. In the context of this problem, that means that we can't really say that they improved their scores or their times on the obstacle courses. Now for the p-values, we do, now for the p-value, you're going to be feeding in a t value, which we just had. T I'm going to use is approximately 4.461. And remember, the p-value is an area, so we want the CDF. So I'm going to go to second distributions, and I want number 6 for TCDF. So 6, enter. Here, we want the area off to the right, since this is a right-tailed test. So my lower will actually be 4.461, and then my upper will be at positive infinity. So remember how you put the positive infinity 1 little e above there, and then put 99. The degrees of freedom, you need to do that one. So put 7, and then enter your way out of this. 0.0015. So remember, we put 4.461 to infinity, 7. That's because when you do this t-value here, let me draw it real quick. When you specify the t-value of 4, that's way over here. The p-value is that little area in there. And so it gave you, let me have it again, 0.0015. What was alpha in this problem? Alpha equals 0.01. We can see alpha is a lot bigger. P is less than alpha, which implies that we reject H naught.